this question in like a general programming interview might be asked in the context of is a particular set of characters within a string, like do a character search in a string. So this question is kind of the embedded engineering equivalent of, given an 8-bit pattern, find that pattern in a bit stream. So this question isn't saying, given an 8-bit pattern, find an aligned 8-bit match. It's given, let's say, 64 bits, any set of 8 bits could potentially match that 8-bit pattern and return the offset of the first match in that bit stream.
So do we have a size limit on the bit stream? Like, is it coming in online, or is it, what do they mean by offset?
Excellent question. I think maybe to generalize this question a little bit is, how do we get this bit stream? Like, how are we getting it? Is it already just one big byte array as we're getting it? Are we getting it byte by byte? That sort of general question of how are we getting it and how do we reference it needs to be asked. And let's say, hypothetically, going back to black color, let's say that the way that you get data in this bit stream is byte by byte. So let's say that they've provided a function called getByte. So they provided a function called getByte, and you call that function, and it returns the next byte in the bit stream. So the very first time you call this function, it's going to be giving you bytes 0 through 7. The next time you call the byte, this getByte function, it's going to return the next set of bits. So you're going to need to keep a kind of running counter of how many bits you've read through so far.
And then offset means the very, like a number of the bit that starts the pattern. Is that the idea?
Exactly. So let's say in this hypothetical case that your bit pattern started, or the first where you found it was bits 3 through 11. You'd return the value 3 for the bit offset where your pattern where the given pattern begins. So going out on a limb here, people might recognize that you could potentially just implement this as some sort of double for loop where we treat both the bit stream and the pattern as bit arrays and just do lots and lots of iterations over it to figure out whether or not it matches using some combination of masking, shifting, and copying. There's some potential optimizations we can do on top of that. But before we get into optimizations, let's see if we can just kind of come up with a basic implementation that would work. And let's see here. I actually wrote up some code. Let me share the code that I wrote, and let's talk about that as opposed to coming up with it on the spot here, just for the sake of time. Come back over here. Is the size of this text good, by the way? I should have asked earlier as well. Okay, I'm gonna take it as yes, it's good enough. So let me talk through what the code I've written is, and this wouldn't be unreasonable code for someone else to write as well. And here I have this getByte function I mentioned before. I happen to implement it so that I could run my code and test that it works. Obviously, if they just gave you the prototype, then you would just need to implement against it. But my getByte, if you pass in data, memory for a byte, it returns that byte. And in my case, I have it return a bool for whether or not whether that byte is valid. In other words, are we done with the bit stream? Assuming there's some sort of end. How did we know when we're done? When getByte returns false. So I happen to implement it and just put 8 bytes worth of data in there so that I could give it a try. And the tricky part about this implementation is trying to deal with reading one byte at a time in a way that doesn't involve reading or doing a comparison multiple times. In other words, what I want to try and do here in this implementation is still compare one byte at a time. You could do it one bit at a time. For every single offset within the byte stream, you could do a bit search for 8 bits. In other words, have a loop checking the first bit, checking the second bit, checking the third bit, and checking the fourth bit, and so on. But what I want to try and do is check one byte at a time. And we know the system is capable of checking one byte at a time, but as we just talked about with memset, we only can compare one byte to another if those 2 bytes are both aligned on an 8-bit boundary. Let me try and say it a little bit differently. Let's jump back over here. If I have let's say I have these 16 bits, and I have my 8-bit pattern. So that's my stream. This is my pattern. I want to compare and I want to search for where is my pattern in the bit stream. Obviously, in this very first exact case, it's trivial. I can compare this byte to this byte using regular equal kind of semantics in C to confirm that whether these bytes are the match or not. But now, how do I check the next set of bytes? Now I want to check these 8 bytes. I want to shift it over by 1. And how do I check these 8 bytes? This starting offset is no longer an aligned bit value. We're now starting at bit 1 as opposed to bit 0. So I can't just say, is this byte equal to that byte anymore? Because that no longer works. So what I need to do is shift. What I've decided to do is I'm going to shift my bit stream over by 1 bit. First, I check the first 8 bits, then I shift my whole bit stream over by 1 bit, and now I can do this comparison again. And I can similarly, on the next iteration, have my original bit stream shifted over twice, or shifted once more from the previous loop iteration, and check those next 8 bits. So at every step of this process, every step of this while loop, I am shifting my bit stream over by 1 bit so that I can always compare my pattern byte to the aligned current byte of my bit stream. That's what I'm going for conceptually here. What I've decided to do is allocate on the stack 16 bits to store essentially the current and next byte in my bit stream. But I can only read 1 byte at a time. So I need to both treat this as a 16-bit piece of memory and also treat it as an array of 2 bytes, such that I can continuously call get byte on the next byte once I've done the appropriate amount of shifting. So let's look at this code a little bit. First, I call get byte. I plop it into the first entry in my array, index 1. And then in a loop, I will plop the next byte into my array. In other words, I have 16 bits worth of storage space. First, I get the first 8, well, the second set of 8 bits, then I get the next 8 bits. And then for each entry, what I do is I check, are these a match? If they are a match, great, I return the count. If they're not a match, I shift over my 16-bit memory by 1 bit and then perform this loop again. And every 8 bits, after I've shifted 8 times, I now need to go and acquire another byte again. Hence this loop. So this while loop is saying, after I've exhausted 8 bits worth of data, I now need to fill up another 8 bits. And this one is checking for each bit offset, does this match? The thing I wanted to point out that's tricky with this implementation, this implementation is probably what many people might think of trying to do. But the pitfall here is that in memory, on a little endian machine, the bits aren't stored in the same way that they appear once you access them. So let's maybe jump back over here and explain that a little bit further. If I have, let's go back up here to this example, and I have my 16 bits. That's my 16-bit storage space. And I said every iteration of my loop, I'm shifting that over by 1 byte, so I can easily do this comparison. What you might think is, okay, first I call get bytes, or get byte for this first byte. Then I will call get byte for the second byte. And because I'm always shifting to the left, then what I'm going to eventually need to do, the next time I need to get another byte, I'm going to copy it over here. And conceptually, this is address 0. So back to my array, my uint8 array, oops. You might think, okay, the very first time when I initialize this function from the get-go, I'm going to need to copy into array index 0. And then for all subsequent times, I would copy into array index 1. This referring to array index 0, this referring to array index 1. And this is the big pitfall, that this makes sense conceptually in memory. This is the correct way of thinking about it in memory. This is array index 0, this is array index 1. But remember, it's a little endian, well, at least in this particular example, I'm saying that it's a little endian machine. And in a little endian machine, the most significant bits are stored up here. Which means that if you tell the compiler or the processor to bit shift to the left a 16-bit date field in little endian, what the compiler is going to need to do, or the processor is going to need to do, is swap these 2 bytes in memory and then do the shift. Because in the bit shift to the left, what we expect to happen is this bit right here to get dropped. We expect the most significant bit to get dropped or get pushed off when we do a bit shift to the left. But the most significant bit isn't the one over here, it's the one over here. And that's where life gets really confusing. And that is why on a little endian machine, I need to first copy my data into the first index. And then from then on, I'm always going to be copying data into the 0th index into my array, but my comparison occurs on the first. And this is because our conceptual idea of how 16 bits is laid out in memory is different than how those 16 bits are laid out when you write it out as a regular long binary number. And this bit shift occurs on the conceptual number, not the memory representation. Let me say that again. This bit shift operation is not shifting the memory, it is shifting the number. And the logical number, whether that number you think about it in decimal, hexadecimal, or binary, that logical number doesn't always match the memory representation of that number. I do want to talk about some optimizations to this, but I really wanted to emphasize this as well as being just another variant of a common question that involves understanding type punning, type casting, bit and byte manipulation, and understanding how little and big endian affects the memory layout of your program, or of your data in this case. So this one question that is seemingly somewhat simple involves touching all of these different topics. And that's why these sorts of questions end up being popular in interviews, because they cover so many things in one question. So let me stop now. Are there any questions about kind of this implementation and how I made it do what it does?
Yeah, I have a quick question.
Yep.
So this you went 16 current, right? So that, how do you decide you are gonna give like 16, or like it could be even 32 or whatever, right? Like, so is that defined in the question, or?
Yeah, no, so good. In this question, it's asked for you to match an 8-bit pattern. If you read in 8 bytes, sorry, if you read in 8 bits from the bit stream and then did your comparison and like, oh, they didn't match, and then shifted your 8-bit field over by 1, what is the rightmost bit going to be? It's going to be 0, because you just shifted over to the left. But you don't want it to be 0. You want it to be the next bit in the bit stream. So whenever you're doing your comparison and your shift in particular, you need to make sure that you shift real data into the byte you're comparing against. So I chose 16-bit field because I needed to choose a data type that was at least 8 bits long for my comparison. And because I'm reading in data from the bit stream 8 bits at a time, I need at least 8 extra bits to store the next byte.
I see. Okay. So basically, even from the last bit of the first byte, like plus 8, still 16 is the closest one. So you pick that, I believe, right? Yeah.
Exactly. So if you read in the first byte, read in the second byte, you're going to shift a total of 8 times. Once you've shifted 8 times, you still have a valid something to compare against, even though your second bit is now, let's call it uninitialized. And at that moment, then you can read new data into that empty byte and continue your checking and shifting.
Yeah, understood. Thank you.
So online GDB can you actually switch it from little endian to big endian and back and forth in some way?
Unfortunately, not in, well, at least not that I've figured out in this tool. There are, I think, Compiler Explorer, I think I was able to get it so that it would compile into little versus big endian, but I couldn't actually get it to run big endian. So at the moment, I'm not aware of, there probably is one, but I'm not aware of a tool online that allows you to compile and run big endian code. And not only that, but it also is very difficult to find the compiler online that will compile and run on a 32-bit machine. All these online tools that I could find all use 64-bit machines for their operations. So not to say that there isn't a tool out there, I just haven't found it, in part because I also am mostly working on either a 32 or 64-bit little endian machine. So I haven't really needed it quite so much. But yeah, this, I believe Compiler Explorer, I think there was an option somewhere to switch to big endian. But in this case, I've specifically written it for little endian because that's what this online tool is capable of compiling and running for me. Yeah, I'll leave it at that for now. Any other questions about this implementation and why I did what I did?
What happens in the special case of just a thing, like you only get 1 byte and you're done?
If we only get 1 byte and we're done, in this particular code, we get that first byte, which presumably returns true, success. We get to our loop and it returns false because there isn't a second byte to return. And then this check down here checks whether or not that 1 byte we received matched. If it matched, great. If it didn't match, then, well, there's no more bytes to get. It can't possibly match from then on.
Right, okay.
And I want to compare and contrast this. The conceptually simplest approach to implementing this solution might be to, once again, do that kind of double or triple nested for loop where you do a bitwise comparison. If I told you to find 8 characters within a character string, that might be your approach. You have a double for loop where you're iterating through the 2 loops or the 2 strings. You check whether or not the first character of your pattern matches the current character of your character string. If it does match, you go to the second one. If it doesn't match, then you reset the inner loop and go 1 iteration further in the outer loop. So the way you could implement this bit matching in the same way that you would implement a character matching or a string matching. You could do it the same way. It would be a whole lot of shifting and masking to make sure everything worked, but you could conceptually do it that way. This implementation, I would say, is kind of 1 step up from that, because it's essentially where it's, if you will, O of n in terms of the total number of bits in the bit stream, as opposed to n times n, as it might be if you were doing your double nested for loop search. So what I have implemented here isn't the absolute simplest way of doing it, although I would say that it is a not hugely complicated improvement upon that simplest way.
So between Sunday and today, it seems like the one of the themes is that you, like, all machines kind of have a SIMD operation on bits because you do byte order, or because you have byte operations.
Yeah, so and this came up I found that a number of times on Sunday, and obviously coming up again now, is understanding how all of these things play together. Not just how does type punning work by itself, but like how does it work in the larger context of the memory, and how data is represented and how is it stored, is something that is worthwhile to be familiar with and comfortable with even.
Okay.
Okay, so let's talk a little about optimizations. How could we improve upon this? Let me open up. Does anyone else here have any thoughts about how we might optimize this? Someone asked earlier, why did I choose 16 bits? And I gave you an answer. I chose a 16-bit kind of storage variable because that was the minimum that was needed.
Yeah, got that. Yeah.
Can we take advantage of the fact that our system supports not just 8 and 16-bit fields, but also supports larger data types? Is there anything we can do with that?
I mean, I guess you could potentially do a duplication of the pattern and basically check at two spots at the same time.
And what would that save us? Just kind of going to the next step. What is the double check saving us?
Just a factor of however many checks you do at the same time.
Sure. So the issue with doing 2 checks, well, the issue with literally doing the same check twice is within one memory operation is that it's possible one of them fails and one of them succeeds, but then the overall operation will fail. So right. We potentially still need to check 8 bits or 1 byte at a time, because if we try and check 2 at a time, all that tells us is that, well, most likely all it tells us is it doesn't match at all, even though one of the 2 bytes may have matched within it.
Right, then you have to go and check individually each byte.
Yeah, so that may not actually save us much or anything doing that multiple times. However, there's several aspects of this, one of which is the memory comparison and one of which is the shifting. So you were trying to get at how can we lower the number of memory comparisons, but maybe we can look at it instead of how can we lower the number of shifts. Because when we're trying to optimize it, we can, any sort of optimization is great. It doesn't like we always have to go for memory accesses and stores in terms of our memory optimization. We can also potentially try just in the context of our shift or other kind of arithmetic or numerical operations. So let's say hypothetically we created a 64-bit field, and we copy our pattern 8 times into that 64-bit field. I think just like what you were getting at, just have it be duplicated. But then rather than trying to do a single comparison, which won't necessarily be useful, instead, let's do those essentially 7 comparisons, and then shift once, and then compare 7 times more again. Because in this iteration, we are shifting our bit stream 1 bit every single bit. If we copied it into a 64-bit field and had duplicated 8 times, then we essentially are doing 7 checks and then bit shifting once, doing 7 more checks, bit shifting once. So rather than having an equal number of checks and bit shifts, we can instead have essentially it decreased by a factor of 7 in terms of the number of shifts involved, even though the number of comparisons is still the same.
Can you draw it?
Sure.
I'm not quite clear what they're trying to explain.
Let's treat it in terms of bytes at the moment. We have 2, 3, 4, 5, 6, 7, 8. Let's say we have these 8 bytes of our 64-bit field, and we've copied our pattern.
Can you share your notepad, because it's
thank you. Sorry about that. Too many screens. Thanks for catching me on that. We copy our pattern into these 8 locations. So this is our pattern duplicated 8 times. And then let's also say that we have our bit stream down here. And we happen to have, and we're storing it at the moment in 8 bytes as well. And it is, who knows, it is some arbitrary series of bits. So what we can do is we can check, okay, does this first byte of my pattern match the first byte of my bit stream? Yes or no? And does the second byte of my pattern match the second byte of my bit stream? So on and so forth. I am doing these. This very first iteration is going to be 8, but for all subsequent iterations, it's going to be 7 once I actually start shifting. But do any of these 7 bytes at their current position in my pattern match the bit stream? And let's assume the answer is no. Then what we can do is we can shift the bit stream over by 1 bit. And then we do these exact same, not the exact same, but then we do these comparisons again, while this is staying the same at offset 0, and now this is logically now at bit offset 1. And then we do these 7 comparisons with the bit stream shifted over 1 bit from what it was previously. And we continue to do that 7 more times until we reach the point where on that final iteration, this is at, oops, that's not the right. This is referring to bit number 7 of our bit stream, but we're still comparing it against the original duplicated byte pattern. And after we've done this a total of 8 times, we now, so after 8 iterations, we've checked all 64 bits of bit stream, such that we still had to do 7 times, I don't know, 8 or something comparisons, but we only had to do 7 bit shifts. Does that help at all? Oops, I'm going to zoom now. So
Sorry,
we still have the
just-
same, we still have the
we
same
cannot-
idea as before, where we have our
Yeah.
our pattern, and we have a bit shift. Oh, sorry, a bit stream that's getting shifted. But rather than
My
having to
own-
shift the bit stream one
Yeah.
bit every time we check, now we can check 7 times and then shift by 1. And after we've done that 7 times, we will have completely checked that 8 byte portion of the bit stream.
So we check first 7 bytes of a 64-bit stream.
Yeah, technically we're checking 8 bytes at a time, but because once you start shifting, you no longer have 8 bytes to check. You only have at most 7 bytes of fully valid data to check. This final byte of your bit stream, if you say you're copying it 64 bits at a time, after that very first iteration starts having some useless data, so you can't check against it. That's why I keep saying 7 so many times. But that's the idea here. So this is one potential optimization by changing both the data type of our pattern and our bit stream in a way that doesn't decrease the number of checks, but decreases the arithmetic operations associated with each check. Another potential optimization or approach you could take to this, and we talked about this on Sunday, is using some sort of a lookup table. So we could, our code here, we were having to shift every single time. We were having to shift our bit stream every single time because we needed to have our memory aligned correctly. Because we are only able to do a byte-to-byte comparison if both of those bytes are aligned on a byte boundary. But what if we instead created a table where one entry in that table is the original pattern, and then the next entry of the table is the original pattern shifted over by 1. And the next entry is the pattern shifted by 2. And this table is going to be a uint 16 data type table. So now we're going to have 8 entries in this table. Actually, I think probably 7 entries in this table for all of the different ways this particular 8-bit pattern could be located in memory. Once again, of our bit stream, we don't know if that pattern is on a 0-bit offset or a 1-bit multiple or a 2-bit multiple or so on. So let's create a table that has our pattern at each of the possible offsets that it could be within our bit stream. And then what our loop looks like is we mask some portion of our bit stream, and then we can AND it against each entry in our table. And what that ends up doing is for each byte, for each set of 8 bits, in the original implementation, we were doing a check and a bit shift for every single one of those. With this possible optimization, we are doing a mask and an AND for each one of those entries. Which may or may not actually be faster than what we had originally. It somewhat depends on, is there a difference in speed or processing time for these different operations? But the point still stands that this might be an optimization using a lookup table that we pre-computed with our matching pattern. So I wanted to give an example of how that kind of well, in this case, it's the dynamically generated lookup table, but it's roughly the same idea as the 256 entry table that we talked about for several different problems on Sunday, and how we can make that be useful. One advantage of an eight entry lookup table is there's a decent chance that can all be stored in registers, as opposed to a 256 entry table is most likely going to have to be in memory somewhere in your cache. So you probably wouldn't have that same downside of the memory access cost using this lookup table, just it being so small. Any other questions about this exercise, just this challenge? And I'm sure there's other optimizations that can be made as well. These were just some of the ones that came to my mind as I was working through this problem. Okay, well, we are over time. It is almost 8:10. We will potentially be seeing each other again on Thursday, so there's an opportunity to ask more questions again. Before we leave tonight, though, are there any other kind of final questions or clarifications that people had about anything we've discussed so far? Or any concerns?
Hey, sorry. Hey, Glenn. Sorry, I might take like extra 2-3 minutes, but this is regarding the structure topic which we discussed about flexible array. I didn't get a chance to ask that time. In the chat, I pasted like a small like a packet with length. Then the data which it gets is like of size length, like and then you have like a CRC. Then how do you frame the structure? Do you use flexible array in this case, or you can use a pointer to represent the data?
So data 0, data 1, and CRC are the three fields, or at least three stated fields of your structure. Is that correct?
No. So each so data 0, data 1, and it will go on till like say length will indicate there are like say 100 data bytes, and it's like a stream of data. So the data 0, data 1 can go all the way till 100 depending on the length.
So your question is that if each of data 0, each of data X internally contains a flexible length.
Like say if this is a structure which we get via an UART or something, how do we capture it? Like do we in a structure, like how do we capture this? Like do we use a like a struct with length uint8 data with flexible array, or you use a pointer to represent the data? And because the size of that is unknown, right? Like
that's a good. What's the best way of doing this? So my first instinct is simply to treat this as a completely byte array. Let's just call it data. And this data has however many bytes. I don't know if that is supposed to be a maximum of 255 or whatever it is, however many bytes it has. And if I wanted to iterate through these data, then my thought would be that data 0, for instance, would need to have a length and a payload, something like that. So what I would need to do if I was going to write a while loop that iterated over all of your data objects, I would want to keep a current pointer and that current pointer would have underneath it this length. And then in order to get to the next message, I would essentially say current equals or plus equals, oops. I would increment current by that length. I feel like I'm saying that in a somewhat unclear fashion. Let me try saying that again. Just because we have things like flexible array members or even structures in C doesn't mean that they're always the most efficient way of representing somewhat arbitrary data. So let me give you a more practical example. In the H.264 standard, there's a number of different payloads within each message. And you can think of those as being data 0, data 1, and so on. They have arbitrary length and they represent the different types of data, but they're all within one big message. And the way H.264 distinguishes between data 0 and data 1 is it puts a particular byte pattern. I want to say it's something like that. It puts that delimiter in between each entry in its message. So when you're parsing the message, you do what we just talked about a second ago, a search for a bit pattern, and you continue the search until you find this bit pattern, and then you know that everything before then was one submessage, data 0, and then some number of bits or bytes coming next are going to be part of data 1. And then you have the same delimiter between data 1 and data 2. So rather than using a structure to try and represent how data 0, data 1, data 2, and so on all relate to each other, H.264 uses a delimiter between each one of those. And you do a simple bit pattern search in order to figure out where the end of data X happens to be. So that's one way of doing it, one real life way that H.264 does it. Another possibility that you could take is you could say, let's scroll down a little bit. We could say we have data 0, and right before data 0 is length 0. And then right after data 0 is length 1, and then data 1. And then length 2 and data 2. And so on down the line. So for each component of your overall message, the first thing you do is you read that first length, and then that tells you the length of data. And you know that the length for data 1 will come immediately after that, as will data 1, and so on down the line. So that's a way of delimiting using an explicit length value for each entry, where each entry in an arbitrary length message, where each entry within that message is an arbitrary length. So I realize you asked, how can we use flexible array members to represent this? But my initial thought is that flexible array members probably aren't the right thing to represent this message in a C sort of pattern. And you'd be better off with a data structure that is something more in line with this, with maybe even ignoring the payload. Because all you really care about is where the data starts and something like the length beforehand. And using a flexible array member might be overkill for that particular need.